Hey guys, I am attempting to go through your lecture with you on, I think it's called Screencastify through Google. So bear with me. I'm new to using this. I've actually just figured it out within the last couple of days. Hope you guys are doing good. I wish we were at school instead of in this situation, but it is what it is. So I'm hoping I'll see you guys after break. I don't know what the situation's going to be at that point. But we'll see. I'm still holding out hope because I would much rather be there with you guys than here at home doing this with a computer screen. Okay, so we're going to start talking about earthquakes. And we're going to talk a little bit about what a fault is. A fault is actually an area where you just have a break in a body of rocks where one slides past another. A lot of people confuse fault lines with plate boundaries. It is not the same thing. A plate boundary is totally different. That's where you have two plates interacting with one another. A fault is just a break in rocks where movement occurs. One body of rock can slide past another. We have four different types of faults we're going to talk about. There's a normal fault, a reverse fault, a thrust fault, and a strike slip fault. And each of these are different in the way that they move or the angle that they exist at. So in a normal fault, we got one side, which is called the hanging wall, and it's going to move down relative to the footwall. And it's called a normal fault just basically because it moves down. It's caused by tension pulling apart. If you're pulling two things apart, one's going to move down. And an example of this would be where we have the Great Rift Valley of East Africa that we talked about, where we have divergent plate boundaries moving. Now, like I said, it's not the fault is not the same thing as a plate boundary, but we do have this type of fault where we have rifting occurring. So this is a normal fault, and as you saw, this we call the hanging block. It hangs over the footwall. This side over here is the footwall. This is the hanging wall. It hangs over top of the footwall, and it's moved down relative to the footwall. So that's what we call a normal fault. And again, it's due to tension. So that would be like the pulling apart of two things. So that movement causes an earthquake. Now, those plates in that plate boundary do not have to be anywhere extremely close to the fault. Reverse faults are a little bit different because instead of moving down, your hanging block's going to move up relative to the footwall, and this is caused by compression. So what type of plate boundaries do we have where compression is going on, where we have two things coming together? That would be your convergent boundaries. So when plates are pushing together, we have compression, and this would be common in the Alps and the Rockies. So if we look here at this little video clip, it shows you how the hanging block, which is on the right-hand side, is moving up relative to the footwall. See how this angle goes down like this? That's how you know this is your hanging block and this is your foot block. This is the side you could walk down. Okay, so we call that our foot block. A thrust fault is just a type of a reverse fault, but the angle is really, really low. So it'd be like a low degree angle. And again, it's caused by compression. So two things being forced together like a convergent boundary. Strike slip faults. These are kind of like when you think about your transform plate boundaries where you have two things moving past one another. It's due to what we call shear stress. And an example of where we see this would be along the San Andreas Fault. This is going to show you the movement. So this is a horizontal movement rather than something moving kind of up and down. These are moving side by side. All right, so what do we define an earthquake as? Well, The earthquake is just the vibrations that you feel when we release that energy along rocks where they are, or along those faults where those rocks move. So when those rocks move, it creates energy, which in turn you would feel as a vibration, which is what your earthquake is that you're feeling. So, what causes earthquakes? Well, they're pushed and pulled by plate tectonics. Now, they don't necessarily have to occur right along a plate boundary, but they do occur near plate boundaries. So, if we look at the Earth's plates, let's kind of go back and think about those different plates we talked about before. And this lays out all the different plates: the North American, the Eurasian, the South American. You can see where plates are moving past one another along the coast of California. Here you have that transform plate boundary, and we have the San Andreas fault line where we have a huge break in the ground rock and the bedrock, and you have an area where one piece of rock is sliding past another. Okay, and over here in Africa, we have some rifting going on this coast. We have some convergence here and some convergence here. Sometimes we have earthquakes that are in the middle of a plate. So if we go back one, we have earthquakes around here in Indiana. Now, are we located near a plate boundary? No, look how far we are. But sometimes we have these earthquakes that occur along these plate boundaries that we don't really know a lot about. Like, why is it happening? How is it happening? And these are typically caused by compression, by some sort of compressional stress within the earth. When we talk about the elastic rebound hypothesis, this is just basically the idea that rocks are deformed, they break, they release energy, and that releases the vibrations that we feel. When we have earthquakes, we have foreshocks. Foreshocks typically come before a major earthquake. A lot of times people talk about foreshocks being smaller. Same thing for aftershocks. After a major earthquake, you can have smaller earthquakes that usually occur. And I hate to use the term smaller because when we're talking in scale of earthquakes, they can be almost as large as the initial quake itself. So these can still be very strong. If we're talking about earthquakes, we have to talk about the study of earthquakes, which is called seismology. And seismologists are people who study earthquakes and earthquake waves. But seismology is the study of earthquake waves. And there's a lot of reasons we study earthquake waves. We've learned already that earthquake waves tell us about the layers of the earth, what kind of materials they're made out of. We look at how fast these different P waves and S waves move through the interior of the earth, and we can determine what those layers are made out of. Are they solid? Are they liquid? And seismographs are what we actually use to record the earthquake waves. So a seismograph, this is kind of like a basic seismograph illustration, and this would typically be attached to the ground, not on a building, not sitting on a building floor. Because if it's on a building surface and anything in that building moves, it would pick up vibrations from the building itself. So these are typically attached somehow to a concrete pad or something that would be attached to the ground and down inside of the ground and protected in some way. So we need to keep in mind that a seismograph is the instrument that records the waves, but a seismogram is the actual, I guess you could say, like the paper that you would get or the recording that you would get, whether that be electronically, which a lot of them are now. The old days, this is the old style where you get a little line drawn. The newer ones are computerized and typically would draw out a line. You would get like the waves on your computer screen. Now, it's going to show you 3 different types of waves. It's going to show you surface waves, P waves, and S waves. And these actually are in order here at the bottom, the order of arrival. The waves that are going to travel the fastest are your P waves, which are called your primary waves. Your S waves are your secondary waves. And then you have your surface waves, which are going to come along last. But we can use the differences between these P and S waves, like time differences, on how fast they travel. And you can kind of tell how far away the epicenter of an earthquake is from your location by using these P and S waves. So this is just showing you a seismogram, and this is what a seismogram basically looks like today. And you can kind of see here, there's no activity going on, and then boom, your primary wave. So that indicates an earthquake. Then your secondary wave hits, and then your surface waves, which are much more destructive, and they're the last ones to come in. We can measure this time distance between the P wave and the S wave, and we can determine how far away we are from the epicenter of an earthquake. So if we're in Versailles, Indiana, and we pick up this seismogram, our seismograph picks up this distinctive pattern of waves, we could use this data along with other points of data to determine how far away we are from the earthquake. Now, this says this earthquake was in Juan Mayen Island on June 15th, 1995, and it was a magnitude of 5.0. But if we can make it back to school, I will show you guys something called triangulation, where we actually use 3 points of data and determine where the epicenter of an earthquake is. So we would take the seismographs from 3 different locations or 3 different cities. So let's say we had a seismograph in Versailles and one in Indy and one in Louisville, and we collected seismograms from an earthquake as far away as Japan. We could take those three seismograms and determine how far away we are from our epicenter of the actual earthquake that occurred. So I think we're going to stop here, and I am going to go over the different types of waves with you possibly tomorrow. So I will talk to you guys tomorrow and have you finish out the rest of the assignments for today.